Good evening, everyone. Welcome to CON329. My name's Omar Lari. I'm a business development manager at AWS. Today we're going to talk about running Kubernetes at scale at Square. So as part of my role, I get to work with customers all around the world as they adopt container services on AWS. And today I have the privilege of being joined by Jeff Flaherty and Jay Estrella from the Cash App team at Square. And we're going to kind of talk about how they've leveraged EKS to move some of their production applications on top of. So just a brief agenda of what we're going to cover today. I'll talk briefly about what is EKS, what is Kubernetes, why we built EKS, and how our customers are using it. And then I'll hand it off to the Cash App team, who will give you a real-world practical example of how they've implemented this as part of their core stack. What you should get out of today is a clear understanding of what EKS is, what Kubernetes is, and then just some real-world examples of how you may be able to leverage this inside of your own environments. So one of the questions I get from customers all the time is, what's best practice for running containers or doing this specific action? To which there's not really a perfect answer, right? There's so many different ways to do things and so many different options that you have that one person's best practice is another person's anti-pattern. So it's really hard to give clear prescriptive guidance on this is exactly the way that you should run containers. However, we do have a few emerging trends that we see that are kind of common and can be broadly applied to all of our customer base. I think the first major point of this is automate everything, right? So you want to automate as much of your infrastructure and as much of your stack as you can. So that means not just your application, which we're all kind of accustomed to automating and doing through CI/CD processes, but also your infrastructure, your logging, your monitoring, your security. The more of that you have defined inside of code, the less error prone and more repeatable that is. So automating everything is a really core piece of being able to scale your application and do that effectively. Another core piece of this, which isn't practical for everybody, is to kind of organize your teams in smaller kind of two pizza teams, right? So you have teams that can work independently of each other. They're decoupled. They can release features independently of other teams. This not only increases the velocity which you can release at and introduce features and functionality to your customers, but it limits your blast radius as well, right? So if you're deploying smaller pieces of code, less places for things to go wrong, and just makes things a lot easier to roll back and fix. So yeah, so a couple of just key things that you see up there on the screen, right? Model all your infrastructure as code. Give your developers as much insight into the application and into the stack and the infrastructure that they can so they don't need to ask you questions. So what is Kubernetes? So this is a 300-level session. I'm assuming most people in the room know what Kubernetes is, and you've kind of come to learn a little bit more about EKS and how to actually use it. But just to get everybody on the same level playing field, right? We know that Kubernetes is an open source application that helps you run distributed applications. So includes things like resource management, scheduling, scaling your containers on top of EC2 instances, and really managing that underlying compute as you scale out. Next, it gives you a lot of built-in functionality around things like autoscaling and health checking, self-healing functionality that can bring your containers back to life if they die for some reason. A lot of these just core primitives and building blocks that you would otherwise have to build yourself, you just kind of get this out of the box, right? So it's really nice for you to be able to start modeling your applications in a containerized world without having to build all this undifferentiated heavy lifting and building a lot of infrastructure that is not core to your business. So some of the key patterns that we've seen across our customers and how they're leveraging Kubernetes and containers inside of their environments. So obviously microservices is a very obvious pattern, right? Microservices and containers just kind of go really well hand in hand together. You can break your monolith applications or develop new applications in just very small, independently deployable pieces, stateless applications, APIs, a very obvious common pattern that kind of containers were made for, if you will. Platform as a service is another very common pattern that we see. So we'll see centralized operations teams kind of abstract away some of the complexity that's involved with running containerized applications. So as the Square folks will talk about today, it's like you don't want every single one of your developers to need to know all the ins and outs of Kubernetes or any container orchestration system. You want them really focusing on business code and the value that your organization actually brings, not the underlying infrastructure details. So we see a lot of customers building platforms on top of EKS to kind of abstract away that complexity and allow their developers to really focus on the business value that they bring. Enterprise app migration, another common pattern. So we see, as I talked about with microservices, is kind of building these small services, but also bringing over monolith applications into Kubernetes and into EKS and being able to take advantage of some of those core primitives without having to rewrite the application. So things like scaling and auto-healing can take advantage of a lot of this functionality without having to rewrite the application and solve some of your problems with infrastructure. So this is another really common pattern. And one of the things that we didn't expect to see when we first launched EKS is actually machine learning. So it was really surprising to us to see that a lot of our usage was being driven by P2 and P3 instance types of the GPU instances. And as we kind of dug into this a little bit further, we realized that, hey, Kubernetes provides a lot of good extensibility for you to plug in open source machine learning frameworks like Kubeflow for customers to build, train, and serve their models around. And this has been a really prominent use case for us for allowing customers to build these dynamic machine learning pipelines on top of Kubernetes. So what exactly is EKS? Before EKS came out, there was a lot of different ways to actually deploy and build Kubernetes on top of AWS. But you were always responsible for kind of the day two operations, right? So a lot of tooling would help you get the cluster up and running, get your clusters running. But you were responsible for upgrading, managing, maintaining, ensuring their availability. One of our main core tenets for EKS initially was we want to provide a highly available control plane for customers so that they don't have to worry about all of that kind of undifferentiated heavy lifting of managing and maintaining all of that core infrastructure. So today, every time a customer, when they do a create cluster inside of their account, for each cluster, we create a distinct set of instances for them. And that includes a highly available etcd cluster, so that's where Kubernetes stores all of its persistence and state. And then we also deploy highly available Kubernetes components, so all of the API servers, the schedulers, the controllers, all of that is provided in a highly available fashion, and then they're exposed through a network load balancer. And that's where that's the endpoint that you use to connect any of your client tooling, like kubectl, any of the client SDKs, and then all of the node infrastructure also connects to that. So kubelet is configured to connect to that endpoint. And we manage all of the TLS to make sure all of that communication is done securely from our account into the customer account. So basically, every single cluster that you create gets its own dedicated control plane. When we set out to build EKS, we had a few core tenets. First, which I mentioned earlier, is that we built EKS to run production-grade workloads. And what does this mean? It's a highly available by default, right? There's no development cluster or a small cluster. Every single cluster that you get gets its own dedicated set of resources. And we always take operational stability and security as our #1 primitive. So anytime that's kind of not where it needs to be, we'll drop anything and make sure that it is where it needs to be. So we really take the security and operational excellence very securely. And we've done really well on this over the course of the past year and a half of building additional functionality around doing upgrades for your cluster and managing the entire lifecycle of that control plane. And I'll talk a little bit about how we've expanded that into the node infrastructure as well. Second is that we provide a pure upstream Kubernetes experience. So we run the same Kubernetes code that anybody else runs that you can download from GitHub from the open source project. We're not doing a fork of Kubernetes or running an Amazon version of it. Our customers don't want that. They want to have portability and have that same unified API across any place that they run Kubernetes, whether that's in their data centers, in AWS, on other providers. So it's the same upstream code that you could download and run yourself. Next is that we provide seamless integrations to the rest of the AWS ecosystem. So as we work with more and more customers, they're asking us for more and more integrations. And I'll talk about some of the things that we've released over the course of the last year and a half. but really just treating Kubernetes pods and infrastructure as first-class citizens on AWS and giving you access to the rest of the AWS ecosystem to integrate into your stack. And lastly is that the EKS team actively contributes back to the project. So Amazon's been building distributed systems for years for customers as a service, so things like S3 and Dynamo and RDS, obviously EC2. We've had a ton of learnings around building those systems, around security and operational performance. And so we're contributing all of those learnings back to the upstream community to make sure that Kubernetes is stable and secure and can run in a similar fashion that we're accustomed to. So kind of a year in review. So we released EKS back in June of 2018. A lot of different things have kind of come out since then. I'm not going to read each one of these out to you word by word, but you can kind of see we've made a lot of improvements to the ecosystem as a whole on top of EKS. An important thing to notice here also is that a lot of these tools are open source. So even if you choose not to run EKS, you can still take advantage of some of the tooling that we've built inside of your self-managed clusters. But a lot of the stuff that you'll see here is things around regional expansion, so expanding into additional markets in EMEA and APAC, obviously North America, South America, releasing new versions of Kubernetes and making sure that those are available to our customers. One thing that's not on the list here that we actually just released a couple weeks ago at KubeCon is the ability to manage the nodes in your environment as well. So not only do we manage the control plane, but we manage the provisioning and the life cycle of the actual compute infrastructure in your account as well. So these are all really things that are important to our customers, things that we've listened to their feedback, asked them what they want us to build, and incorporated those into the product and the service. One thing I'd also encourage you to look at is we were one of the first teams within AWS. We actually were the first team inside AWS to open source our roadmap. So we want to be completely transparent with everything that we're building and really engage with the community. So you can actually go to our GitHub site today and see, not just for EKS, but all of our container services, what it is that we're working on and what we're building. So this is all based on customer feedback, and we'd love to have you engage here. So if you see something, or if you don't see something that you think should be on there, I would encourage you to open an issue. And we'll mark that as investigating, and we want to engage with the community here to make sure we're building what our customers are asking for. These are some of the highlights of what we've released from the roadmap. So just a brief overview of what you'll see on our open source roadmap. Some of the things that we've recently released, as I mentioned, managed node groups, so managing the lifecycle of the nodes inside of your account. IAM roles for service accounts. This was a big ask for our customers, right, is how do I control what my pods are able to do inside of AWS and what AWS API calls they're allowed to make. So this is an example of what we've done in the open source, built this. You can run this in self-managed clusters inside of EKS, but really brings that seamless integration to make Kubernetes a first-class citizen on AWS. Support for new versions. We actually have 1.13 and 1.14 that are available today, with 1.15 coming soon. Some of the things that you can see that are coming soon, I think a big one that a lot of customers are anticipating is Fargate for EKS. So this is a lot of engineering effort that we're putting in today. This will allow us to manage not just the control plane, but actually the EC2 infrastructure as well. So you really can just come in and define how you want your pods to run, how you want them to scale, how you want them to be exposed through ingress controllers or service meshes, and you don't have to actually manage the underlying EC2 infrastructure. So this is a really exciting feature that's coming for us soon. As we kind of look on to next year and over the next 18 months, some of the additional things that we're going to work on are things like managed add-ons. So these will be things that are either AWS-centric, so integration with CloudWatch, or open source-centric, so integrations with things like Cluster Autoscaler. So things that we can actually manage on your behalf without you having to install yourself. And so a lot of work will go into improving the UI and the UX around some of those add-ons and some of those additional services, and then some additional things there, regional expansion and UCNI plugin. With that, I'm going to hand it off to Jeff, who's going to talk a little bit about the platform that they've built on top of EKS.
Thanks, Omar. So what is the Cash App? If you'll indulge me for a moment, let me set the scene. It's Friday. You wake up to a $15 Cash App notification. A pal paid you back for that pizza you shared. Your balance now reads $172. You use your new money to get $1 off coffee with your personalized cash card. You even hit up the ATM after. 5 p.m., direct deposit hits. Do you buy Bitcoin, or do you cash out to another bank instantly? With the Cash App, you decide. Some fast stats for the Cash App. Each month, over 15 million users make or receive payments through the Cash App. We're number one in the finance section of the App Store, we're proud to say. And this year, we announced more than double year-over-year growth in quarter one, and we booked over $250 million in revenue in quarter two. Suffice it to say, we're growing like crazy. As the popularity of the Cash App increases, we need to scale not only our infrastructure, but also increase developer velocity. So, for the rest of today's talk, we'd like to tell you all about how we're meeting these challenges. Specifically, with the Cash App platform, which is leveraging EKS. First, before I start describing the platform, I think it's important to set the stage and talk a bit about the core values that inspire it. First and foremost, you maximizing developer velocity because hiring is much harder than making your current engineers more productive. Secondly, security is every Cash engineer's responsibility, full stop. And this is reflected in our platform as well. Third, we value leveraging managed open source infrastructure. Managed because more of our engineers' time can be spent product. Open source, for one, to support the broadest availability of developer resources, so think Stack Overflow. And two, to limit lock-in to the operational rather than the architectural. Finally, we believe in infrastructure as code. This means code reviews, reproducibility, and tests. Ultimately, this is what allows us to treat our platform as a high-quality product and make operations completely self-serve. In order to realize these values, our small team of plucky engineers has built a platform on top of Kubernetes by leveraging AWS managed services wherever possible. Using a combination of Go and Terraform, the main feature highlights of the Cash App platform are, 1, security. AWS IAM and Kubernetes RBAC combine in some very compelling ways to harden a soft multi-tenancy environment. 2, autoscaling. From pod to cluster, no human intervention is required to meet our peak demand in the middle of the day or to save us money in the middle of the night. 3, metrics and alerting. Things inevitably go wrong. Bugs will be introduced. Without a comprehensive metrics and alerting system, did that tree really fall in the forest when no one was around to hear it? 4, logging and tracing. Once you know something is wrong, you need the tools that'll help you triage exactly what's going on. New services get provisioned with first-class log search and tracing support out of the box. And finally, and arguably the most important feature of the Cash platform, our comprehensive self-serve tooling for provisioning and maintaining services. Putting together all these features using AWS and Kubernetes will look something like this. This is a regional view of the Cash App platform and the embodiment of the values and features I've just described to you. At the heart is Kubernetes and EKS. We extend Kubernetes capabilities with AWS managed services such as RDS, SQS, and Amazon Elasticsearch to create a complete and comprehensive application platform. There's a lot going on in this picture, so let's break it down feature by feature. Security, first. With EKS, Kubernetes role-based access control is tightly coupled with AWS identity and access management out of the box. We combine this with AWS Simple Token Service via our own on-premise identity solution. The result is finely grained access control via temporary credentials that's protected with multi-factor authentication. This all integrates seamlessly with the way we do things on-premise already, and it makes the transition to the cloud frictionless from a security perspective anyways. Specifically, we link Kubernetes RBAC with their RBAC roles with their on-premise counterparts by way of a special purpose IAM roles. Some well-defined configuration connects the two inside a Kubernetes config map. The end result is clearly defined RBAC roles for owners, deployers, and administrators alike. Services also need to authenticate themselves to use Amazon resources external to Kubernetes. Currently, we use IAM credentials mounted as Kubernetes secrets to either access AWS resources directly or indirectly via Secrets Manager in the case of those services which require their own credentials, such as Aurora. These credentials are only ever stored in two places: secrets for the pod that are accessing the service, and in Secret Manager for rotation, coordination reasons, and indirect access, as I talked about earlier. Rotation is performed frequently via a periodic job. The simplified pseudocode job looks something like this. For each service, we list the access keys and check if they are active in a couple different ways. First, by examining the access key directly. Second, by using Secrets Manager's metadata. We also check if the secret is being used in Kubernetes via the Kubernetes Go SDK. This is why they're stored in Secret Managers to begin with. And finally, we check if there are any old pods lying around for some reason that might still reference an old secret. Once this is all checked, we can now begin rotation by using the Amazon and Kubernetes SDKs to create a new key and wire it all up. Once rotation is done, all inactive keys can safely be deleted. Now, obviously, this rotation process is a bit complicated and less than ideal. Now that IAM roles for service accounts are available, we'll be improving this flow significantly. Note, however, that we'll still need to store things like Aurora database credentials inside of Secrets Manager. The next important feature of the Cache App platform is autoscaling. In Kubernetes, we scale our services by making use of the horizontal pod autoscaler. However, in order for the HPA to work effectively, you need to have a reserve buffer capacity available at any given time. We ensure this reserve capacity is available by using what we call placeholder pods. These pods have the lowest priority of any pod in our system. And as soon as a service needs a pod, they get evicted. Finally, as the placeholder pods themselves become unschedulable, the cluster autoscaler kicks in and expands the EC2 autoscaling groups. The goal of this autoscaling setup isn't to burst instantly, but rather to ramp up as traffic increases. For those who didn't catch all that, let's walk through an example of autoscaling in action. Here we have 5 nodes with 4 pods running on each. 2 of those nodes only contain placeholder pods. My service, labeled MS, has 8 pods and an HPA managing it. Currently, the HPA is configured with a CPU threshold of 80%. Once the aggregate threshold exceeds 80%, in this case 5, a calculation is performed to determine the number of pods required to bring the aggregate back down under 80%. As a result, 2 more pods are added to the service. However, there's currently no available capacity. This is why you see these 2 pods without a home on the right. The Kubernetes control plane kicks out 2 placeholder pods in favor of the service. Now it's the 2 placeholder pods that are without a home. This is when the cluster autoscaler kicks in and requests a new node by increasing the desired count on the associated EC2 autoscaling group. The unscheduled placeholder pods now have a home, and I won't go through a scaling down example. However, suffice it to say that scaling down works in a similar fashion, although it proceeds a lot more carefully. The next piece of the puzzle is metrics and alerting. It goes without saying that having metrics and associated alerting tied to your service is essential. Fortunately, Kubernetes has a great story with Prometheus. Normally, you would pair Prometheus with Grafana. However, in order to maintain consistency between our on-premise and cloud metrics, we send metrics to SignalFX. Signal Effects then integrates with PagerDuty, which rounds out our alerting story. Conceptually, this is how everything is set up from a high level. Prometheus is running inside Kubernetes. However, it runs on a separate managed node group, which itself is managed by a separate EC2 autoscaling group. Prometheus scrapes the metrics from all the pods in the cluster, and they get sent up to Signal Effects. The Prometheus operator makes managing Prometheus itself straightforward. Our open source service containers expose metrics using the open metrics format. We then use a custom resource definition to tell Prometheus which pods it should look for and what port it should scan the metrics from. A bit of relabeling is used to organize things. The end result is every time a new service is provisioned, metrics get aggregated automatically. For node-level metrics, we use the Prometheus node exporter with a pretty standard configuration. Once Prometheus aggregates these metrics, they're sent to Signal Effects using the Signal Effects gateway provided as a Docker container. In order to generate the Signal Effects dashboards, we use Yelp's SignalForm Terraform provider and provide service owners with some sane defaults. Owners wishing finer-grained control of their dashboards can extend our base Terraform configuration themselves without us ever getting involved. The end result is automatically generated dashboards that look something like this. So the pager is going off, the system is down. Panic has set in. Fortunately, we've got our engineers covered with logging and tracing features of the Cache App platform. With our platform, whenever you provision a new service, all its logs will automatically get sent to Elasticsearch. This is achieved by using FluentD as a daemon set and using the FluentD Elasticsearch plugin to send all the logs to Amazon Elasticsearch Service. Finally, service owners can view and search their logs using either Kibana, which Amazon hosts, or using Loquacious, our open source log viewer that is designed specifically for outage triaging. I should also note that by request of our users, we also send logs to S3 for cold storage and longer retention. Here's what Loquacious looks like. It makes it easy to search by error, by container, by host, by any metadata you've attached to a bit of logging. And it's fast. When the pager goes off, Loquacious is often our engineer's first destination. Our tracing system is pretty straightforward. We use the Jaeger open source project to provide traces. The Open Tracing client is embedded directly into our open source Kotlin and Go service containers. A bit of configuration points them at Jaeger, which is running as a service in Kubernetes. Here's an example of what a trace looks like. To give you a sense of how important these traces can be, recently we used them to diagnose and solve a performance issue. The solution resulted in a 50% performance improvement in one of our most critical pathways. Traces are the type of thing that when you need them, you need them. So it's important to have them out of the box and ready. The final feature that I'd like to highlight today is our self-service tooling. Creating services as a developer is as simple as running a single command. The provisioning server does all the work. You specify the name of the service, the environment, and the owner of the new service. In the background here, we can follow along with the provisioning process as it makes its way through setting up the various Kubernetes and AWS resources the service will need, as well as connecting everything up to the features we've been discussing previously. Don't worry, I won't force you to watch the whole thing, but we're proud to note that the entire process takes under 2 minutes and is completely self-serve. Creating a database is also a simple matter of specifying what you want. The name of the service you want the database for, the environment, how many replicas you want, and finally, the DB name itself. Again, in the background here, we can see the service provisioner creating the necessary resources in AWS and uploading the corresponding secrets. Now, I'll turn it over to Jay. He's going to share his experience of moving on-premise applications over to this cloud platform.
Thanks, Jeff. The platform is empowering us to break apart our monolith and to move faster. In the last year alone, we saw an explosion of new services running in AWS. By removing friction, we encouraged more experimentation, making engineers the arbiters of their own velocity. We've provisioned over 105 services in the last year alone. And Cash App has learned lessons about scaling and is including those lessons in our framework MISC. MISC treats database sharding as a first-class concept and provides job queues, leasing, metrics integrations, and envelope encryption all out of the box. The Cash App platform makes it easy to play with an idea to see if it works. Because the cost of experimentation is so low, it's been easier to break apart our on-premise monolithic services. This is allowing us to switch to a different architecture, an event-based one, that lets us trade strong consistency for eventual consistency and higher availability. Under this new paradigm, a service that is the source of truth for a particular domain object publishes an event when it has been updated. For example, when a payment is initiated, we publish a payment initiated event, which contains all of the payment information that could be useful to another service. Other services then subscribe to these events. The events get consumed and aggregated or transformed based off the service's local data, and a copy of that event should not be stored to its database. Specifically, the events that we subscribe to are not updates to state or transformations. It's an event that contains the entire domain object. Though ultimately, our mobile apps require a synchronous call. They'll call to a service, and that service has a transformed version of an event it had received in the past, and it uses that to answer a query. An RPC we receive could lead to new events being created and enqueued. So let's dive a bit deeper into breaking up our monolith. Cash App has plenty of services, but two are significantly larger than the rest. One of our monoliths takes all app traffic, has its own logic, also calls out to other services. And doing a deploy of this service takes up to 2 hours of engineering time. But it's often the easiest place to add new code. So our cloud platform is ready, provisioning a new service is easy, and getting something deployable is easy. But it takes time to spread expertise and discover and solve the new problems we have from a more distributed system. So we're building primitive services to make doing common things easier, constructing a series of screens, adding content to the activity feed, sending notifications, and performing authentication. This, in turn, will encourage other teams to spin out parts of the monolith that they own into their own services. So, when deciding what to remove from our monolith, we're considering things like the amount of load we could remove, the amount of data we'll need to migrate, and how often that code is being changed. We also hope that we can migrate an entire domain object into its own service, rather than just using an API to a database. After we've identified what data we need to move out, we do an initial backfill of that data from one database to our new services database using an HTTP-based backfiller called Backfill. So all writes from the monolith to data owned by that new service should include a write to the new service as well. We then perform a diff across the old data and the new data to ensure both sides are in sync, or we can explain any conflicts. We then switch the source of truth to the new service and continue dual reading and writing, and eventually we'll delete the old data, delete the old code from the monolith. We're rinsing and repeating this process to curb the growth of our monolith and to break out more services. So here's an example of a piece of our monolith that we broke out. We have 2 notification services, Postmaster, that aggregates information needed to render notifications, common things like a customer's name or address, email address, and Raven to provide a way to interact with our different SMS, email, and push providers. Services store some templating information, and Postmaster itself also holds some templating information. That all gets combined, and then a rendered notification gets passed through to Raven, which translates that notification to a format for our providers. For example, after a payment is made, our peer-to-peer service would render a partial template, pass it along to Postmaster, which would then fill in the rest. If Postmaster is behind in processing events, we may see stale data, but it will eventually become consistent. So let's talk about what happens when you send someone $5. So your friend tries to send you money. It first hits our monolith, and it'll call out to 3 other services. First, we call out to an authentication service, which follows the JSON Web Token standard, and then a service that owns the storage of a truncated, hashed version of a customer's contact information to see if this payment is spam. And then finally, a service to determine if any user-provided information is required to complete this payment. In the happy path, we don't need any extra information. Otherwise, this could include screens like whether or not we need someone's social security number, or an explicit confirmation that this is the person you want to send money to. And one last thing. We're committing to open sourcing as much of our cloud platform as possible. We'll be open sourcing our Kotlin-based Kubernetes-aware service container called MISC, our data migrator called Backfilet, and Logquacious, the fast and simple log viewer we talked about earlier, when we didn't find any modern minimalist web user interfaces designed for read-only log exploration. We built our own. So check it out if, like us, you index your logs in Elasticsearch too. Cruit, a toolkit for building real-time user interfaces for Kubernetes operations for situational awareness. Pictured here is our plugin for viewing all the nodes in a cluster by the health of the pod on that node. This comes in handy when you're updating the AMI of your worker nodes. CSOP, the cache service operator, a self-contained operator for managing services that provides features like auto-deploys, canary deployments, and a GUI dashboard. Thanks. And as time permits, we'll stick around for any questions you have. Can I take it?